Okay, so good morning, everybody. This lecture today will be for our course on modern physics. Will be on the quantization of light, and particularly this lecture will be on photoelectric effect. Okay, so this one is about the photoelectric effect. We have already studied how the electron was discovered, meaning the quantization of electric charge. When we studied the black body radiation, we saw that the classical explanation of a very simple, apparently simple phenomenon, which was the emission of light by heated materials, had a behavior as a function of the wavelength that couldn't be explained with the classical physics. And so Planck solved the problem by introducing something very strange, which was that the oscillators in the material emitting light, these oscillators, they had some quantization of their energy, okay? And so it perfectly explained the body radiation, but there was no further comprehension of what it meant, okay, to quantize the oscillators in the material. So the next effect, which is the photoelectric effect we are going to see today, is something that completes, okay, the discovery of this first quantization, okay, of the oscillations. And it was Einstein who explained this effect. So this is actually a very classical effect, okay? So I have, let me diminish here maybe, okay, the size. We have the classical evacuated recipient, okay? This is a normally a glass one, because you need to see through it, you need to send light. So this is light, okay? You send light to a metallic cathode, and you have a pump to have some basic vacuum inside, so as to not be in, so as to have no other effect interfering with the effect we want to study. And which effect is that? You have some two electrodes, the cathode, the anode, and you have some voltage between them. We call it V. And the anode here in this configuration is actually some kind of grid. Okay, the electrons, okay, which will be emitted by the cathode, will pass through the anode. They will be accelerated or not to the anode, and they will pass through this hole. And so after that, there is no electric field here, and they will be detected here at the end of the recipient, the glass bulb, as a current, okay? So what do we have here? What is classical, what is understood at this time, it is that you have an electromagnetic wave, the light, okay, transports energy. This energy is transferred to the electrons in the emitter. See, I don't call here cathode and anodes, because actually it will be the emitter, okay, and this will be the collector. Or so we have emission of electrons, And these emitted electrons, they have a kinetic energy K, okay? So K for each emitted electrons is half the mass of the electron, which has been discovered, remember, with the Millikan experiment, times, okay, the velocity of the electron, okay, squared. Okay, so as there is a voltage between the two electrodes, the electrons are accelerated in the large sense, meaning this acceleration can be positive or negative, okay? So it's accelerated by the voltage V, okay, to the grid A. And so, as I said, the electrons are measured as a current. I will call it I, okay, by an electrometer, which is connected to alpha here, okay? And so this is a schematic representation of the effect. You have a metal surface. You need a metal surface, so you need 3 electrons. You have incident light, the energy transferred to the electrons, and the surface emits electrons, and you detect them. Okay, so what is the strange thing about that? Everything is very well understood, and so what the people at the time they measured the current here, I, okay, as a function of a few parameters, a few variables. So you measure it, of course, as a function of the voltage V between the two electrodes. They measure it as a function of the cathode material, but this is something really, at the end we will see it. They measure it as a function of the parameters of the light. So you have two things. You have the intensity and you have the frequency of the light, essentially, the color of the light, okay? And so first let us explain what is expected when we vary the voltage between the electrodes. So the electron, let's say the voltage is positive. The electrons emitted here, they are attracted to the anode, okay? And so they will have an acceleration, they will have an increase in their, a variation at least, in their kinetic energy. And so we apply here the work kinetic energy theorem, which says that the variation of the kinetic energy is equal to the work, okay, of the force acting on the electron, okay, between these two electrodes. So we have the variation of the kinetic energy Ka minus Kc, okay, final minus initial, okay, and this is equal to the work of the force. So the force is E. This is E is positive here. This is the elementary charge of the electron. We know that actually this is the charge of the electron is minus E. And so this is EV. Okay? And okay, so how do we know this is EV? You can say this is the work of, no, this is not this is the work, okay? The force is E times the electric field, and the electric field is the voltage divided by the distance between the electrodes. And so when you multiply, okay, the force by the distance to have the work, so you have this function, this expression, okay? And so let's have a look at this equation. Okay, we can see that, okay, this is the positive value of the elementary, okay, charge of the electron. And so if the variation of kinetic energy as the signal of the sign, sorry, of the voltage. So if the voltage is positive or 0, okay, this means that the final kinetic energy is higher, okay, is bigger than the initial one, and so you accelerate the electrons. And when I say all the photoelectrons are detected, all the photoelectrons that pass through this grid, through this hole, obviously, okay. So they are accelerated, and you will detect them all. So what you expect is that for this positive voltage, you will have some saturation, okay, of the current, because you will detect all the photoelectrons. If the voltage is negative, you will have a decrease of the kinetic energy between the collector and the emitter, okay, and so that not all the photoelectrons will be detected. Why is that? Because actually you have some distribution of kinetic energy for the photoelectrons emitted. Some are slower, some are faster, and so if you have some acceleration, okay, negative acceleration, some of them they will be stopped before passing through the collector, okay, and so they won't be detected. And so you will only detect the fastest photoelectrons, okay? And in the limiting case where you have they arrive here with Ka equal to 0, what I told you, they won't be detected. And so you will detect no photoelectron at all if this voltage is such that even the fastest photoelectrons, okay, they are stopped here before passing this grid, okay? So we have no photoelectron. And so if we try to we use this relation between the voltage and the kinetic energy. The kinetic energy, I remember you, it is always positive or 0, okay? It cannot be negative. So we call V naught, okay, the stopping potential. And so this stopping potential corresponds to, actually this is already the max, okay? It is when even the fastest electrons, okay, their initial energy, okay, is equal to EV0, okay? You just have to put it here, okay, and you will see that Ka equal to 0, the fastest photoelectrons, okay, arrive here with Ka equal to 0, so minus Kc max equal to minus EV0. Why did I write minus V0? Because I want V0 positive, okay? So the applied voltage actually is minus V0, okay? And so the final equation is this one. E, the elementary charge of the electron, the elementary charge, times the stopping potential, okay, both positive values, is equal to the maximum kinetic energy of the photoelectrons, okay? And so this is okay. The scientists at that time already had this knowledge, okay? They could apply this. And so let's go now to the next measurement, okay, of the photocurrent I as a function of, let's say, the light intensity, okay? So what is expected through a classical explanation, okay, is that as you increase the intensity, I remember you that I call intensity, it's a very general term to say that it is power, okay? So this is energy per unit time per unit area, okay? So this is essentially energy. And so when you increase the intensity of the incident light, you have more energy, okay, incident on the cathode, okay. So you should have more photoelectrons, okay, emitted by the cathode. You should also maybe have more energy per electron. And something interesting, as you know, this is an electromagnetic wave. This is an oscillating electric field, okay? Oscillating electric field. And so when you increase the energy, essentially what you increase, so E increasing means the amplitude, okay? The amplitude of electric field increases, okay? So you are increasing the movement, yes, of the electrons, and so they should have a higher kinetic energy when they are emitted by the surface. And so it means that for the sample, okay, you are going to study, you will have a higher maximum kinetic energy, meaning that you will have a higher value for the stopping potential, okay? The correspondence is direct, okay? Max kinetic energy, okay, max stopping potential, okay? So this is what we expect. So we expect to detect this. You have, as a function of the voltage, the photocurrent, okay? So you have some intensity of the light. So for V positive, as I said, all the photoelectrons are detected, so you will measure already, okay? As soon as V is something positive, so you measure all the photoelectrons, so you have some value for the photocurrent, okay? And for the negative, what you have, so this is V equal to 0, okay? For the negative, you will have, you will diminish, okay? You will see a decreasing of the photocurrent because some of them, the slowest photoelectrons, okay, they will be stopped before reaching the anode, okay. And so if you increase the negatively the potential, okay, there is some time you will have the stopping potential minus V01, because if you increase more, already you have stopped, okay, even the fastest photoelectrons have been stopped here. If you increase the intensity of the light, so you will you expect to observe a higher, okay, value of the photocurrent, okay. This is what you expect, and you expect also that the photoelectrons will have a higher maximum kinetic energy, and so you will have a different value, okay, of the stopping potential, a higher value of the stopping potential. This is what you expect. This is not what you observe, okay? What you observe is this one. So what is striking here, okay, here is okay, you have more photocurrent here because you have more photoelectrons, okay, due to the fact that you have more energy, okay, available to emit electrons, but you have the same stopping potential, okay? The stopping potential is independent of the intensity. So what does it mean? It means that you have the same maximum kinetic energy, okay? This is very strange, okay? And so the other behavior that can be observed is as a function of the light frequency, okay? So you will illuminate your cathode with blue light, with red light, okay? And so what do you expect to observe? Nothing special, okay? Because if you change the wavelength, meaning the frequency, okay, of the light, it is not expected that the energy of the light depends. The energy is not expected to depend on the frequency, okay? And so you don't expect anything special. You change the frequency, and so you will observe effect as a function of the energy, okay, of the intensity, okay, but not as a function of the frequency. But what you observe is this one, this thing, okay? We have three frequencies here. First, let's begin with F1, okay? This is a frequency. Let's say it's something like a green frequency, okay, a green light. And so you observe, you have some, obviously, every time you vary one parameter, okay, so you vary the frequency. You have to be constant, okay? You are not varying the intensity. You will observe the phenomenon for the same value of the intensity, and for also obviously the same material. And so for a given frequency F1, you observe what you already know. So you know that you have here all the photoelectrons detected, and as you increase negatively the voltage, you will have the stopping potential for this frequency, okay? And if you increase the frequency, okay, so you had sort of, let's see, this is a green light, okay, and so here you put something like blue, okay, and so you have a higher frequency. Okay, why do you observe this is not expected, okay? Why do you have more photocurrent? There is no reason. And more strikingly, you have a different stopping potential, meaning that the photoelectrons emitted with blue light, they are more energetic than the photoelectron emitted with the green light, okay? So this is the first thing. You have the intensity, okay? And the third thing is, if you put some, you decrease, okay? Instead of increasing the frequency, you decrease it, and let's say you go to the red, okay? And so there is some frequency here when you won't observe, okay? You won't have a stopping potential. The stopping potential will be 0, and you have, if you have something F less than Ft, F smaller than Ft, T is for threshold, okay? And so you have no effect, okay? So this is what I wrote here. When you increase the frequency, you increase the stopping potential, meaning that you increase the maximum, the kinetic energy in general, and the maximum kinetic energy in particular. And you observe threshold frequency, and if the frequency of your light is smaller than this threshold frequency, you won't observe the photoelectric effect, okay? So classically, this is really no explanation. Einstein understood it, so it is one of his 1905 papers, okay? Remember, there are three very important papers, publications of Einstein in 1905. It is the relativity, okay, the restricted Brownian movement, and the photoelectric effect. And he won the Nobel Prize for this explanation of the photoelectric effect. So Einstein says he generalizes somehow what Planck had said about the oscillator in the materials, okay? So the oscillators, they are electrons, and they oscillate when they are, for example, submitted to an oscillating electric field. And Planck had quantized this oscillation. Einstein goes further. He quantized the energy of the light emitted by these oscillators, okay? So he calls this a quantum of light. He calls it I don't know if he calls it, actually. We call it now a photon, okay? So this is a quantum of light, okay? And so what is quantized? This photon, it has an energy epsilon, okay? And it is proportional to the frequency, okay? And the proportionality coefficient is the Planck constant. Okay, and so let's see what are the implications of this quantization of the energy of the photons, okay? H is the Planck constant. So what you have the energy when you illuminate, okay? Going back to this experimental arrangement, okay? So you illuminate your material, your metal with light, okay? And so you will have one photon of the light that will transfer its energy to one electron of the cathode, okay? And so, sorry, it is here, yeah. So one photon transfers its energy to one electron. And we have here something which is from solid state physics, okay, solid state physics. And this is the energy, okay, you have the bands, okay, the conduction band of a metal, okay. So here, inside the metal, okay, so the surface is something, okay, this is here, okay, for distance, let's call it z, okay. So for z, and this is 0, okay, and so for z less than 0, you are inside the metal, sorry, and so you have the surface, which is something, which is some kind of interface, okay, and so you have all the electron states, okay, field, okay, the conduction band of the electrons of the metal, okay, and so if you are outside, okay, this is z0, okay, this is the depth. So for z bigger than z0, you have a free electron, okay, so your electron is out of the metal, okay, and so to put an electron from, sorry, I said it was the valence, it's no, I said it was the conduction, but it is the valence band, okay, so you have to give this electron here the energy, okay, let's say it is here, okay, your electrons is here, it has the highest energy possible, okay, in this state, and so you give it some energy, let's say this is the energy of one photon, hf, and so it had initially this energy and now it has this one. So part of it was used, this one is what we call phi, okay, this is the work function. It is used to for the electron to get rid of the attraction, okay, of the other charges in the material. And once it got rid of this attraction, so he is free, okay, to fly, okay, in your evacuated glass recipient, okay. And so what does it do? What does it do with this the energy? It didn't use to get out of the metal. It is used as kinetic energy, okay. So you have this very simple equation that the energy of the photon was used to for the electron to get out of the metal, okay, so the value of the work function, it depends on the metal, okay, and give it some kinetic energy. This is the mass of the electron, and this is its velocity, okay, soon after it got out of the cathode material, okay? So this equation is here. So you have the kinetic energy K, okay, which is the energy of the photon minus the work function, okay, needed to get out of the metal, okay. So this is the equation of the photoelectric effect, and if you understand it, okay, this is an equation of energy conservation, okay. So this is very simple, and if you understand it, and okay, let's write it here. So you remember, oh, so sorry, this is max here, it is not any kinetic energy, okay. So this is the stopping potential. We saw that EV0 is equal to the maximum kinetic energy, okay. And so we can write, okay, this one, we write it in this form now. It is HF, the energy of the photon, okay, minus the work function of the surface. So if you draw, okay, the stopping potential V0, okay, so you have this equation, E V0 equal to HF minus phi, okay. So if you have here V0, you can write it here, H over E minus phi over E, okay. And so this has some unit, okay, which is joule, okay. This is an energy. Actually, you will see what we use electrovolts, okay. I will talk about it soon. So you have V0 as a function of the frequency of the light, okay. So you see this is a constant, Planck constant, the elementary charge, okay. So this is a constant. And so what you have is a straight line, okay. And the slope of this line, what is the slope here? Slope, this is H over E. So if you don't know what the value of H is, you can measure it, because we already know what the value of the elementary charge is, okay. And so let me write here these values. E. I will write it very okay, not the full value, 1.6 10 to the minus 19 Coulomb, okay. And the Planck constant, we already have a value of it. I don't know if you remember, but what was the first value measured for H? It was measured when the spectral power, okay, of emission of heated of the black body, okay, radiation, was measured as a function of the wavelength or the frequency, okay. And so we already had a value for H, and obviously this is the same one here. So this is 6, let me, 6, it will not give the exact value, 10 to the minus 34, okay, joule second. And now I remember you that these two values are, so this is approximation. I didn't write all, okay, the numbers, all the digits, okay, but both E and H are, let me, are exact values now, okay. I won't write exact here because the exact values are not this one, okay. They are more precise values. Okay, so you have you can measure here, for example, the Planck constant. This is some very interesting, very simple experiment. Okay, you can do with a photoelectric cell. Okay, and you measure. So you have to have some tunable light source. Okay, some which is not obvious actually. Okay, and so with that you can measure the Planck constant. Okay, so the last thing you can do, you can measure as a function of the material. So we have here a table. So for these elements, sodium, cesium, cadmium, aluminium, okay, all metal, you have the work function, which is given here in electron-volt. Okay, what is the electron-volt? The relationship between electron-volt and Joule is 1 electron-volt equal to 1.6 10 to the minus, okay, Joule. Okay, so when we calculate here, okay, the kind of voltages we use in this experiments of photoelectric effect, okay, there are a few electron volts, okay, so in Joule they are very small, okay, so this scale is more adequate, okay, for this kind of problem. So we will make some problems, okay, we will solve some problems, some exercises in our class, okay, and so we will learn how to use, okay, this equation, okay, and deduce some interesting properties of materials, etc. And okay, so I finished here. This is bibliography for essentially the illustrations, okay, of this lecture.